Hi everyone, and welcome to what I think is my very favourite bit of physics, if not my favourite bit of science, actually, kind of ever. So I'm really disappointed that I don't get to teach you this in the classroom because I do think it's really, really interesting and super quite remarkable, really. It is a lot of information. So I'm going to go through a few things. I'm going to go through mass and weight again. I'm going to go through what we call free fall. I'm going to go through Newton's three laws, how we put things into orbit, a thought experiment by Galileo, and one by Newton. And finally, but very briefly, I'm going to go through what weightlessness is. So when you see astronauts floating around in spacecrafts. So there is a lot of information. There is some maths in this as well. And you have to kind of park your mind a little bit in terms of sometimes some of the concepts seem really quite illogical and counterintuitive. I'm going to try my best to prove to you that these things are correct. But it is one of those things that you just have to kind of go with. The more you think about it, the more you'll see that these things are true. So really exciting stuff. I love this stuff. So let's introduce three people. I'm sure you've heard of all of them. So this person here, I've got a funny colour. I don't want that colour. I'm going to have purple. So let's go to purple. There we go. This person here is, I know why. It's because I'm not on a pen. Let's have a purple pen. Sorry. This person here is Aristotle. Now, Aristotle is a very, very famous Greek philosopher. Lived a very long time ago, 384 to 322 BC, a long time ago. And he had some very interesting theories about falling objects, which is why I'm going to talk about him a little bit later. Then we've got this guy here. This is Galileo. Galileo, also very famous physicist. We talked a little bit about Galileo the other day. We were talking about the universe and the theories behind the solar system and how the solar system all works. And we're going to talk about a thought experiment he did. And then we've got, of course, we're doing a forces topic, really. Isaac Newton here at the end. Okay, now they are in order of when they lived. So as I said, Aristotle, really, really long time ago, in 384 to 322 BC. Galileo was 1564 to 1642, and just after Galileo's death, we've got Newton, 1642 through to 1726. So the ideas, the timeline moves with the ideas. Okay, now I think Galileo is fairly remarkable because, as we know, Newton is credited with huge amounts of physics around the forces stuff, and Galileo's theory, which is actually turns out to be correct, and I'll get onto that later, was obviously thought of before we knew about forces as such. So really, really interesting stuff, this, and it links very closely into why we're in orbit around the sun, the moon is in orbit around us, and how we put things into orbit, which is why we need to learn about it in this topic. So let's have a look at Isaac Newton. Now, he has three very, very famous physics laws, okay? And I'm going to go through each one and try and explain it a little bit more, so you know what they mean. The one that we're really interested in, really, for the orbits, is the first and the second law. Okay, the third law is useful to know, but it isn't particularly relevant in this setting. Anyway, here is his first law. An object either remains at rest or continues to move at a constant speed unless acted on by a force. Okay, so what we're saying is, if there is an object with no force on it, so let's imagine a ball, let's imagine it's just in space. If it has no forces on it, which it doesn't because I haven't drawn any force lines, then that ball can either be at rest, stationary, or going at a constant speed. This links very closely. If you think about what we were talking about when we were talking about cars, we were saying balance forces, stationary or constant speed. It's the same idea here. Basically, that's where that idea comes from. Now, this is, again, you're going to have to go with me on this. Let's imagine that somehow this ball is kicked in space. Now, at the moment that the ball is kicked, a force is applied to it. Okay. Now, as soon as the amazing person who seems to be able to live in space, as soon as their foot leaves the ball, that force is no longer there. Okay. So it's quite a common misconception that forces kind of keep acting and peter out over time or something. It is either there or it isn't there. So at the point where it's kicked, where there is contact between the ball and the foot, there is a force. As soon as that foot goes away from the ball, then the force is no longer there. But what it has done is it has started a ball moving. That ball will then continue to move at a constant speed in a straight line forever and ever and ever through space with no extra forces acting on it until something happens. So it hits something else, and so another force is applied and it moves off in a different direction. And we've done this kind of idea before because we talked about particles in a gas moving in straight lines unless they hit something else. That is why, because of Newton's first law. Okay, it's the same kind of idea if you imagine, we did this as well back in October, the book on the table idea. Now, obviously, we've got the weight down and the reaction force up. We've done this before. But if we imagine the horizontal, the side-to-side forces, when there are none, which there aren't in this diagram, then we're at rest. There is no force, it's at rest. If we had a car sat on a pavement in the same idea, parked, we'd have the up and down force, which we tend to ignore because they're not relevant to the movement. And then it would be stationary. If we had balance forces on the car, then we would expect it to be going at a constant speed. So they're all those ideas that we did last time in the last topic. Even though I didn't explicitly tell you at the time, we were basically learning Newton's first law. Okay, the second law is a maths equation. Okay, so the force on an object is equal to the mass of that object multiplied by the acceleration of the object. Now, this clearly means that we need to understand what acceleration is. Now, acceleration is a change in speed. So when we're talking about constant speed, then what we're saying is there's no acceleration, there's no change in speed. So it's going constant speed of, let's say, 10 meters per second. If we went back in 30 seconds, it's still traveling 10 meters every second. If we went back in half an hour, it's still traveling at 10 meters every second. Acceleration is different. What that means is something is either increasing in speed every second or it's decreasing in speed every second. Okay, so the unit for acceleration is actually meters per second. Okay, so let's give an example. Let's say the acceleration was 1 meter per second. That means, let's say it started at 10. A second later, it's increased to 11. A second later, it's increased to 12, and so on and so forth. Every second, it's increasing by 1 meter per second, every second per second. Now, actually, there is a better way of drawing this unit than seconds, meters / seconds. So what we do is we say meters per second, and then per second is like squared, okay? Meters per second, meters per second squared, okay? So really interesting unit. Speed, remember, is in meters per second, or some kind of unit of distance and time. Distance divided by time, meters per second, miles per hour, kilometers per minute, anything. So long as you've got a distance and a time, it's distance over time. Here is another one. Meters per second per second. This is an acceleration unit. This is a speed unit. Okay, so if we were going at 10 meters per second constantly, we had a constant speed, then we're not going 10 to 11 to 12 or down 10 to 9 to 8. We're not changing the speed. That would mean that we had an acceleration of 0 meters per second squared. Okay, this one here, as I said, is 1 meter per second squared, because we're increasing by 1 meter. We're going 1 meter further in every second. So therefore, if we're going 1 meter further every second, we must be getting faster. Because if we were going the same number of meters every second, then we'd be going the same speed, the same distance per second. So the formula itself, the force is equal to the mass of the object times acceleration. So let's consider, and I'm going to draw this very badly, as usual. Okay, that's very bad. That's my car. Okay, even I think that's more terrible than I've ever done before. Never mind. There's my car. So let's imagine the mass of my car was 1,000 kilograms, and it was accelerating at 10 meters per second, 10 meters per second squared. We can use the formula. We can say, well, what's the force acting on the car? What's the engine force? Well, it's the mass, 1,000, times by the acceleration, 10. So the force then is 10,000 newtons. Remember, Newton gives his name to the unit of force. So 10,000 newtons would be the engine force on that car. Now, we're going to come back to this in a little while, but this is one of those formulas, force equals mass times acceleration, which is so important. You're going to use it time and time and time again, like speed equals distance over time. It is one of those things you just need to try and remember, okay? Don't worry if you don't remember it straight away. Force equals mass times acceleration. In fact, I know you've met it before very briefly, because I know that Mr. Morkison used it as an example when he was introducing to you how formulae work and how to rearrange them. We are going to rearrange it in a little while when we come on to talking about falling. Don't worry too much about the unit. This is the one that we use more so than this one. This is technically right, this one, but this is much more well used. So basically, I'm not going to go into why this unit works for the time being, just because I would go off on a little bit of a tangent. But these two things are equivalent. They are the same as each other, but the one that I've circled is the more common unit, but they mean the same thing, meters per second or meters per second squared. If you have a negative acceleration, essentially you're decelerating. So if you've got 0 meters per second, that's no acceleration, no deceleration. 1 meters per second, 2 meters per second squared, 3 meters per second squared, etc. Those are increases, those are getting faster. If you go -1 meter per second squared, -2, -3, going that direction, then you are getting slow, you're decelerating. Anyway, let's move through to the third law. Now, a bit of an odd one, this, because if you just read this sentence, it may not make any sense to you. When one body exerts a force on a second body, the second body simultaneously exerts a force equal in size and opposite in direction of the first body. What on earth does that mean? Now, first of all, it's got this word that I mentioned in the video the other day, body. It doesn't mean human body. It doesn't mean that one human body is hitting another human body. Body is just anything with mass. So we call the planets celestial bodies, for example. They are big things of mass in space. You can call anything a body. You could call a car a body, the earth, anything, okay? So what it's saying is when one thing of mass hits another, exerts a force on it, then the second one also, simultaneously means at the same time, exerts a force of equal size in the opposite direction. Now, in fact, you have already learned this as well. I just didn't tell you that you were learning Newton's third law. And I tell you what I mean. I'm talking again about the book on the table scenario. We've got our book on the table. We have got the weight of the book down. That is, let's just say, I don't know, what's a book, a kilo? Let's say 10 newtons then, down. What I'm saying is, here's my body number 1, that's the book. Body number 2 is the table. So what I'm saying is, if weight 10 newtons goes down, then the opposite body, the table, pushes oppositely with 10 newtons as well. Equal and opposite. Two things, the book pushing down on the table pushing up on the book. Same force, 10 newtons each way, balanced forces, completely stationary. That is all it means. It's just a very odd way of saying it, but that's how Newton put it. Now, the key thing is that the force is equal in size. I'll give you another example. Let's say here's the Earth. Here is you or me or whoever standing on the Earth. Person is body 1. Earth is body 2. Person pushes down on Earth with their weight. Earth pushes back on person by the same amount. It doesn't matter what it is. Let's say 700 newtons. That's much more realistic than 70. 700 newtons, okay? Someone else, different mass. There's another person. Let's say they're heavier. Let's say they're 800 newtons. Earth pushes back on them with 800 newtons. Okay, slightly counterintuitive again, that you might think that the Earth pushes up the same amount on everyone, but it doesn't, because remember, we've got to have balanced forces. So if someone's 800 newtons, they need a balanced force, otherwise they're going to be falling down through the Earth. Okay, so that's what Newton means by the equal and opposite force. You might have heard the phrase, every action has an equal and opposite reaction. It's the same idea. It comes from this the reaction force, the push back. Anyway, let's move on again. Back to something that, again, we've done already. So this is all revision, really. You should. I know you don't know the laws, but hopefully you understand the concepts of the laws because we did them before. Now, we've learnt this before. Weight equals mass times acceleration due to gravity of the planet. Now, last time we met it, I called this gravitational pull. Because I didn't want to have to go into what that means in terms of what that actually means, because we weren't doing about acceleration. I'd have to go into all the stuff that I've just talked about what acceleration is. And actually, all you needed to understand was that mass and weight are different. So if you remember, we had this whole conversation about when you say, oh, I'm going to stand on the scales, and my weight is whatever it is, 70 kilos. You don't actually mean your weight is 70 kilos. You should say your mass is 70 kilos. And if you remember, we talked about the Weight Watchers as being, should be called mass watchers. If you want to find your weight, you have to times your mass by the gravitational pull of the planet. And we did this. We said that the gravitational pull of the Earth was 10. So let's do an example. Let's say if someone is a 70 kilogram person and they are on Earth, then their weight, the force they experience, is 70 times 10. That's going to be 700 newtons. That is their weight. Now, what does that actually mean? Why have I changed this to acceleration due to gravity of the planet? Well, if you imagine there's a cliff, here's some, I don't know, the sea. If we drop something from the cliff, it's going to start falling. It's going to start falling down towards the sea, okay? And that's because gravity is pulling it down. And it's actually pulling it down by a certain amount, which means it will accelerate at 10 meters per second squared. It's going to go 10 meters per second faster each second. So every second it's increasing its speed by 10 meters per second. That's what that means. And that is standard for Earth. It doesn't matter what we drop. It is going to accelerate with 10 meters per second squared. as its acceleration. Now, that leads us nicely onto the next bit that I'm going to talk about in about 5 minutes. But that's what it is. If we were on a smaller planet like, I don't know, Venus, let's say, then the gravitational pull would be smaller. That would mean the acceleration would be smaller. What that means is if we drop something off a cliff, it would fall it would still fall, but it would fall at a slower acceleration. It would still be getting faster, but it wouldn't be getting fast as if it was on Earth. If we dropped it on Jupiter, it's going to get faster much quicker. The acceleration is going to be much, much bigger. So it is just that's what the gravitational pull actually means. And if you remember, we did a sheet where we moved a 50 kilogram mass around different planets, and we had to work out what the weight was, and we were trying to demonstrate that weight is going to change on different planets. The force you experience will change on different planets, but your mass remains constant. So it is not a good diet to go and live on a different planet, because your kilograms, your mass, will stay the same. Okay, so let's go back to our skydiver. We met our skydiver a while ago, if you remember. So let me just have a little sip of water so I don't lose my voice. Just a second. Okay, that's better. So the skydiver jumps out of the plane, which has seemingly disappeared out of view now. What happens? Well, we get a big pull down from the Earth, and the force that he experiences, which will be his mass and the acceleration of 10 because of the Earth, because we're falling towards the Earth, will be his weight. So let's just stick with the number we've been using. So 700 newtons will pull down. When he first jumps out, very little air resistance. So he starts to accelerate down because we've got unbalanced forces. Okay. Now, after a while, the air resistance builds up to match the downwards force. So we end up with 700 newtons in both directions, which means we're no longer unbalanced, we're now balanced. Okay, we've reached a constant speed. So you don't keep accelerating and accelerating and accelerating, getting faster and faster and faster and faster and faster. You get to a point where air resistance balances out with your weight, and that means that you would become balanced in terms of forces, and that means that you would be going at a constant speed. Now that actually has a name. It's called the terminal velocity. It means kind of top speed. In this situation, you can't get any faster than that. It's around 250 miles per hour. So it's very, very fast. That's what you're falling at. Now, if you hit the ground at 250 miles per hour, then that is going to probably result in fairly certain death, which obviously you don't want to do if you're jumping out of a plane for fun. You'd quite like to survive that probably. So what you need to do is you need to change your speed. And how are you going to do that? Well, you can't change your weight. You don't suddenly change weight halfway down. You're still 70 kilos at the beginning and you were at the end. The pull is still 10, so it's going to be 700. So how do you slow yourself down? Well, you give yourself a massive upwards force. So you decelerate. This is unbalanced again. We've got a deceleration. We slow down to a much more reasonable, something like, 15 miles per hour, 5 miles per hour, whatever is a suitable, I don't know what a reasonable speed to hit the ground is. Probably about 5, isn't it? So we've got this massive imbalance. Then what will happen a few minutes later, we've got this huge deceleration. And then after a while, this balances out again. So we go back to 700. So even though we've got the same forces on both of these diagrams, this is now a constant speed, but it's much slower constant speed, much safer as well. Okay, and this kind of starts to demonstrate that actually, if the forces are balanced, there's no resultant force, there's no overall force. It doesn't really necessarily tell us anything. There's zero force on both of these. There's no resultant. We're going down and up in opposite directions, we've got balanced forces, there's no resultant, we're going at a constant speed. Doesn't matter that these forces are the same, 700 over here, 700 and 700 over here. The speed is not the same because of the situation that's been going on. So both the same diagram, both the same forces, different constant speed. So, excuse me, how does this all relate to what we are trying to learn about? Well, we're learning, what I'm trying to allude to is something that, this is Galileo again, that Galileo was thinking about, and he did what's called a thought experiment. He thought about something, and he thought about the result of what would happen. Now, it is generally thought that he didn't really go up the Leaning Tower of Pisa and drop balls off the top of it, although there is some debate as to whether he did this really. So he tried to think about dropping two objects off the Leaning Tower of Pisa at the same time. So he imagined two balls, probably made of something like iron or steel, so heavy balls of different sizes made of the same material. And previous to this, and this is where I'm going to talk briefly about Aristotle as well. Now, Aristotle had always taught that heavier objects will fall faster. Okay, and actually that seems to make logical sense. If you think about dropping a mouse and an elephant off the cliff, which one would hit the ground first? Well, your kind of brain goes, well, obviously it's going to be the elephant because the elephant's heavier. And that is what Aristotle had always taught. It's what people had believed for a long time. And Galileo thought about this and he thought, no, actually, I don't think that's the case. I think that those two objects, regardless of their mass, are going to fall and hit the ground at the same time. Okay. Now, we now know that this is in fact true if we have something called free fall. Now, you can see here I've written what free fall actually means. An object is in free fall when the only force acting on it is gravity. So what we're saying is if we had two balls of different sizes and we dropped them at the same time from the same height and they only had gravity acting on them, what he's saying is they would fall at the same rate. They would fall at the same acceleration and they would hit the ground at the same time. And I'm going to use Newton's second law to demonstrate why this is true. Okay, so he is right, Aristotle is wrong. It should be that they hit the ground at the same time. And I'm going to explain why by using another famous experiment, which again you may have heard of because they did this on the moon when Apollo 15, the moon landing happened, and I'll come back to this in a minute. They demonstrated that Galileo was right using this experiment. So for this one, if we imagine we're just on Earth and we dropped a hammer and a feather. Now, if I did that in the classroom, I think you could probably work out which one would hit the ground at the same time. We'd get this situation. We'd get the hammer falling quicker and hitting the ground first. Okay, so both of them have a force of weight acting down. The feather is going to kind of float around. They've got loads of little bits, haven't they, that kind of catch on to the air particles. We get a big air resistance on that one, not so much on that one. We're going to get this one, the feather going much slower and the hammer going much quicker. And we're going to get this situation. The hammer is going to hit before the feather. Now that's all very well, and we can demonstrate that on Earth. But if we imagine that there is no air, we remove these bits. We're saying, okay, there's no air. What's going to happen then? So when air is, I guess what we're saying is if the hammer fell quicker because it had less air resistance, the feather fell slower because it had more air resistance. So if there's no air and no resistance from the air in play, what would then happen? And this is where we need to come back to and remember Newton's second law. So I'll remind you, force equals mass times acceleration. Now, Acceleration on Earth is constant. It is 10 meters per second squared. 10 meters per second increase in speed every second. Okay, so if you remember, you did this with Mr. Mawson, you can rearrange a formula to show acceleration as so acceleration equals. So the way you do that is we need to get rid of this m. So how do we get rid of that mass? Well, we need to divide by mass because we've got times by mass, and we do the same on both sides. So now we've got force divided by mass, and then we've got rid of mass from there. Mass divided by mass is 1, so we can get rid of it. And we've got acceleration. So acceleration equals force divided by mass. Now let's demonstrate this with some numbers of our hammer and our feather to see if we can see why then they would both fall at the same rate. So let's just give them some mass. So let's say that the hammer is, should we make it 1 kilogram? Okay, nice and heavy. And let's say that the feather is 10 grams. So let's say 0.1 kilograms. So we keep it in the same unit. So we can work out the force, can't we? Because we know that force is mass times acceleration. So we know the force. So we've got 1 times 10 is going to be 10 newtons. So this one's 10 newtons. And 0.1 times 10 equals 1 newton. So this has got a 1 newton force. So the forces are clearly different. The weights are different. So 10 newtons pulling down the hammer, 1 newton pulling down the feather. So kind of, again, if we think about it, we think, oh, well, the hammer must go quicker then. But if we plug the numbers into this one to find out what the acceleration is, so we're kind of doing it backwards, we've got 10 newtons divided by mass, which is 1 kilogram. 10 divided by 1 equals 10, which is the acceleration, meters per second squared. So that's how fast it is falling, or how the speed is increasing. Let's do the same with the feather. We've got force, so that's 1 newton here, 1 newton divided by mass, 0.1. Now, I'm going to tell you that that is 10 meters per second. You may know that already. If you don't believe me, feel free to put that into a calculator and you'll find that that is the case. So even though the force on the objects is different, the mass is different, the acceleration is the same, because essentially you are cancelling out and going back to something that is a constant. A constant in a formula is something that remains the same all the time. It's not like if you think about your maths equations, you've got like your x and y, you try and find what x is, try and find what y is, or whatever it is. If you've got a constant, it's always the same. So on Earth, the A is 10, okay, for falling objects. Now, the formula weight equals mass times gravity essentially is force equals mass. They're the same formula, but you're just changing F to weight and A to acceleration due to gravity. So I could have done this exact same thing with weight equals mass times gravity. In fact, they are exactly the same formula. That and that are the same thing. G is a constant of 10 meters per second. This one, force equals mass times acceleration, this 10 can change if it's like a car moving or whatever, but with falling, G is always 10, okay, on Earth. It would change on different planets. So, if we're on the moon, and they did do this, oh, I can't get my thing over. When they dropped them, they did fall at the same time, and I've linked a video later for you to watch. In fact, there's 3 videos I'd like you to watch after this. This whole lesson is kind of video based. You don't need to do much in the way of writing. You're going to watch this. I'll be finished relatively soon. Then you're going to watch them do this on the moon to prove to you that what I'm saying is correct. Where there's no air, they will hit the ground at the same time. So this is trying to demonstrate kind of they'll be there and then they'll be both there. And then a few seconds later, they'll both be there. So they are in line with one another as they fall. And then there's a really great video as well with Brian Cox, who is a very famous physicist who's alive now. He does the same experiment, not on the moon, but in what we call a vacuum chamber, where they suck the air out. A vacuum is a space with no air in. So they suck the air out and they do the experiment with a feather and a bowling ball, not a hammer, but it's the same concept. And you'll see that everything I've said is right, and what Galileo said was therefore right. So Aristotle, probably on Earth, you could class them as him as right if you're including air resistance, but certainly if something's in free fall, only being affected by gravity, then it will fall at the same acceleration at 10 meters per second on Earth, regardless of the mass. Okay, now when Apollo 15 successfully landed on the moon, we saw this demonstrated by one of the astronauts who was called David Scott, and he genuinely did this and proved this to be correct. So therefore, proving Galileo right. Shame that Galileo was long gone and never got to see that, but he was absolutely right. Here's another demonstration of it. Now, obviously, you wouldn't really want to do this, but if you dropped an elephant and a tiny mouse in a vacuum, there's that word spelt, it means without air, then they would fall at the same rate. And there's my reminder as to why, because if you divide force divided by mass, big force divided by big mass, you're going to get the acceleration due to gravity on Earth, 10 meters per second squared. Little mass and little force divided, doesn't matter, you're still going to get 10 meters per second squared, just like I demonstrated with my numbers before. Okay, so really interesting stuff this, and fairly amazing to think that somebody just kind of thought this through in their own mind, which I find fairly fascinating. So what does this have to do with orbits? So we're going to talk about another thought experiment now. So this time from Isaac Newton. He thought about this. He didn't do it because it would be fairly impossible to carry this experiment out, but he thought about it. And this is called Newton's cannon. So what he imagined is this little picture is trying to demonstrate there is a really, really big mountain with a big cannon on top of it. And he thought, right, if we fire this cannon out, it's going to travel a distance and come down and hit the Earth. Okay, so you can see that in trace A. Then he thought, right, well, what about if I fired this out faster? Well, if it goes faster, then it's going to travel further to the side before it hits the ground. So he thought, right, well, it's going to go further and it's going to hit the ground further away. That makes sense. And then he thought, well, what about if I send it out at such a speed that as it starts falling, it kind of goes along with the curve of the Earth. So this one here is falling down, but because of the curve of the Earth, now obviously if the Earth was flat, so let's say the Earth is flat, it's going to hit the Earth. But because if there is a curve to the Earth, it travels round and it keeps falling. It's still falling, still falling, still falling. Oh, it's still falling. Oh, it's got back to the beginning. And off it goes again. It's falling, still falling, still falling, still falling, and you get the idea. And that is what an orbit is. An orbit is something falling towards another, one body falling towards another body. In this case, it could be an artificial satellite. In this case, it's a cannonball. It goes into orbit around the Earth. We have our own natural satellite falling towards the centre of our Earth all the time. The moon never reaches it though, because it is constantly because of the distance away from the Earth and the fact the Earth's curved. It's being pulled down towards the centre, but it never reaches it. same with the artificial satellites that we've put out into space. Now you've got to get it right, because this one here is saying, okay, this one's gone so fast that actually it's managed to escape the gravitational pull of the Earth, so it just travels off into space in a straight line forever and ever, like we because following Newton's first law. So you've got to get it right. And actually, when you put things into orbit, obviously we don't go up the highest mountain and try and fire them off like that. We actually fire them up at such a speed that as they start to fall down, they never get there. I'm going to go off the bottom. Okay. Oh dear. Oh dear, I've brought on my menu. That's not what I meant to do. Okay, let's get rid of that. There we go. So I haven't managed to go all the way around because my Earth's just a bit too far down. But you get the idea. You fire it off, you've got to get the right angle and the right speed. So you don't want to go up here and escape gravity. You want to get it to be falling down all the time. Falling. Oh, but it never gets there because of the curve of the Earth. And we've got about 8,500 satellites that we've launched into space. And they are there orbiting around our planet. Now, if they start to slow down or they come a bit closer, then they may well come down and fall onto the planet. When that does happen sometimes, and they're usually programmed to do that at a certain time. But most of them are in orbit. About 3,000 of them aren't actually in use anymore. They're just kind of there. But all sorts of reasons, GPS, communications, that's how the sat-navs work, satellite navigation, kind of clues in the name. So yeah, really, really insane that Newton just thought about this kind of in the early, I suppose, 1700s. And yet we're actually now there. And it explains why we're going around the sun. It explains why the moon is going around. And the final thing it also explains is, let me get there, this concept, weightlessness. Now, weightlessness you will experience if you are in free fall. Okay, so if you are a normal person standing on the surface of the Earth, like all of you, you've got your weight acting down, which is a force, as you know, and we've got the reaction force, the equal and opposite action from the Earth, the same amount, and you don't feel weightless because you've got balance forces on you. If you are in free fall, which means that you don't have the reaction force, astronauts are just in this situation. They're falling all the time. Now, remember that the reason they're falling, these people are on the International Space Station, which is orbiting the Earth. So it's traveling. The International Space Station is always falling towards the center of the Earth, but never getting there because of the curve of the Earth. And in doing so, that is also what the astronauts are doing. They are in free fall constantly, which leads them to feel weightless because there is no opposing reaction force to them. So they're constantly accelerating towards the center of the Earth and never getting there because they're traveling so fast around the Earth. So really interesting concept, quite tricky to get your head around. Loads of stuff on that on Google and on YouTube if you're more interested in weightlessness. I'm not going to go into too much detail really now because I think it's not really relevant, because the point of this video is really to look at the laws and look at the why things are in orbit, but just an interesting little bit of information at the end there, hopefully. Right, I'm going to leave it there, guys. Have a lovely rest of your day. See you later.